Okay, here you go.
Very good. All right then. Well, thank you for making it this far into this very nice workshop. Thank you, Asa and Martin, for organizing. This talk, it's going to be a bit of a departure from Christoph's talk.
We can hear you, but maybe.
Oh no, I turned it off. So you sorry.
Now it's on. Excellent. Thank you for the pointer. Good. Yeah. So this is going to be a sort of the first of a dual talk, back to back with Fernando's talk afterwards. So we're going to do basically we're going to look at some concepts related to integrated information theory that Larissa briefly spoke. Larissa introduced earlier, but also with some other perspective, bringing in other ideas from information theory. So in this talk, I'm going to use a bunch of the concepts, the tools that we're going to use, and then Fernando is going to actually put them to use. Speaking of things like causal emergence and things that one might actually care about in complex systems. So this is all again joint. No, that doesn't work. No, it doesn't work.
Put the mouse click on the just the focus is the mouse focus. I think it should be.
Oh, incredible! Yeah, so this is all joint work with Fernando and as well as Shannon Barrett from the University of Sussex, and then a bunch of people from Imperial and Imperial College in Cambridge, all in the UK. Good. So we're going to be talking about information dynamics, broadly speaking. And information dynamics, we can loosely sort of define it as things like studying how information is stored, transferred, and modified in a multivariate complex system. Right? So typically when we think of information dynamics, we have a picture of something like this sort, right? Where you have, say, in this very simple case, 2 time series with 2 variables interacting in some funky way. Throughout the presentation, I'll use the same notation. So the indices denote different variables, like over time. X denotes the past, Y denotes the future. I'm going to keep everything fairly simple, and everything is Markovian and nice. Right? And this is a very general setting that then has a bunch of different applications. For example, stimulus response in a neuroscience type experiment, species and resources in, say, an ecology setting, stock and indices in economics or econometrics, or agents and environment interactions in, for example, in the study of agency. So I'm not actually going to deal with any of these applications in particular, but we're going to develop a bunch of intuitions and a bunch of tools to reason about these dynamics and multivariate systems. So the motivation of my talk comes from a few open problems that I think are still hanging about in information dynamics. And I'm going to list them in the next few slides. So let's take first an example, transfer entropy, which I'm assuming that everyone is more or less familiar with. So it's the information that, basically the conditional mutual information of the past of one variable towards the future of another variable conditioned on its own past. Right? And typically that's seen as this sort of arrow, right? So if you come from the literature like range causality or neuroscience or any of this, you'll see like some form of effective connectivity from one variable to the other. And that's all perfectly fine, but there's some issues with this. For example, things that we can have information transfer, with this thing being greater than 0, without having mutual information. And that's kind of tricky, and I think that's sort of a problem. So there's... Yes?
That's very strange.
So you can totally have this if, for example...
Is that the normal? Is that really the labeling you wanted? I mean, like maybe it's not wrong, but
is it?
I'm kind of surprised that X1 and X2 are on this.
Yeah, so X's are the past.
Past. Okay.
X's, so time goes left to right. Okay. By the way, so I have quite a bit of material. If I don't get through all of it, that's fine. Make sure you interrupt at any point if things don't make a lot of sense. So yeah, throughout the presentation, time goes left to right. X's are the past, Y's are the future, and the indices are the variables. So this is the mutual information, the past of one with future of the other, condition on the past of that other thing. And you would get this, for example, if Y2 is the XOR of the past of the system. Right? So this kind of thing can happen, and then that really makes me question whether, I mean, there's nothing wrong with transfer entropy per se, but I really don't want to attribute it to this one particular arrow. I don't like this being a property of these 2 variables, like being drawn in that way. So one problem there is how to describe information dynamics, because clearly these things cannot be drawn as a conventional graph. I think sort of the this typical picture we've been seeing, I think it's very incomplete. Another issue, for example, now going back to these notions of integrated information, let's say that we try to think about integrated information phi as a total strength of interactions between different parts of the system. And one big disclaimer, I'm considering all these systems of two variables, like two time series. So there's a huge amount of research by Larissa and other people on how to partition the system and find the complexes and yada, yada, yada. That is super important, and that I'm completely sort of ignoring here, as I'm considering the much simpler case where I already have just two variables and one unique split point, and I want to put a number to phi. So in some work by our colleagues, Asfuni and Professor Murray, and now Tia, they think of phi as sort of deviations from independence, right? So you have a system that has all these connections or all these interdependencies, and then you cut through these in some way, and you find some sort of statistical projection. How far is the actual system from an independent or disconnected system? And you call that phi. And that, again, is actually a really good idea. This is a super elegant paper in PNAS 2016. Thing is that actually there's many ways in which the system can deviate from independence. So you can still compute these, but what could still happen is that if you want to make a statement such as this system integrates more information than this other system, it may be a bit of an apples to oranges comparison. And we'll see a clear example of that later. So now the issue is, how do we define these things? So at the moment, I don't, and even more broadly, I don't think there can be any single universal measure of integrated information. As the final problem, again, let's say that we measure something like phi, or so when we think of information dynamics or complexity or any of these things, we typically have a picture like this of a cup of coffee. We have the coffee on one side, and then a coffee mixed with milk on the other side, and there's sort of a fully ordered and a fully disordered system, and then some funky stuff happens in between. And it's in that middle point where there's complexity or whatever you want to call it. So typically when we reason about things like a curve of phi as a function of the regularity of the system, we want it to be 0 there, and we want it to be 0 there, but it can't really be whatever in the middle. We don't actually have meaningful ways of constraining what these measures do in anything but the extremes, right? So we're basically fitting a function based on your boundary conditions. And I think this is related to, for example, some of the questions that came up after Larissa's talk, which are, the specific numbers for these phi measures or some other measures of information dynamics. They don't yet have an operational meaning. Like, for example, what does that mean for phi or transfer entropy or any of these to be like 0.4? We don't actually have tools to, yes.
Can I ask a question for confirmation? So is it a subjective value or objective value? So that phi is, for me, it has information, or it is objectively have information?
So here I'm taking phi to be some phi-like measure. I mean, there's some sort of there's still research on what's the best way of computing phi, such a thing. So I'm taking this as sort of rough, some phi-like measure. I don't know if that's what you mean.
It's an objective
number. You compute this number according to some algorithm, and it's the right one.
Yeah, so we're trying to define measures that capture something like phi.
Is it observer dependent or not?
Yeah, at that point.
Oh, depends what you mean by observer dependent. I mean,
let's say no.
Let's say no, but
I think no. No, I mean, we computed. We are observers, but nothing. I mean, since if there's anything that can compute something, you need something that can compute the number. So if that's an observer, then it's observer dependent, no? But not in the partially observable case. Not partial observable.
Okay, thanks.
Yes.
What are necessary properties of this phi? I mean,
that's a very good question. So typically, these type of papers will start with these sort of minimal requirements of like phi being 0 when the system is in a fully ordered state, and phi being 0 when it's in a fully disordered state. And then there should be some sort of peak in the middle of some sort.
and it's the only necessary.
Well, that's the thing. So I don't think there's more like agreed strong prescriptions of this is what a phi measure would do. I mean, if you look at say the IIT 3 papers, they do have a bunch of axioms, especially related to conscious experience, because it's primarily intended as a theory of consciousness. But it's not entirely clear to what extent those axioms actually translate to mathematical requirements. I think that's still up for debate. Okay. So yeah, as a final problem, I'll say that we still don't know very well how to measure these things. So most of these measures of information dynamics, phi and others, lack a clear operational meaning. Okay. So in this talk, so the take-home message of this talk is going to be, first, the information dynamics are actually richer and harder to characterize than previously thought, and that the, or at least a way of going forward is to narrow down what we want to measure and how. And I think partial information decomposition, or PID, is a really good way to do this, and I'll give a brief introduction to PID later in the talk. So I'm going to split this talk in 3 parts. I don't know how far I'll get. Probably not to all of them, but part 1, I'm going to introduce the concept of synergy and redundancy and put them in context with neural complexity, or IIT 0.1, in case some of you are familiar with it. Then in part 2, I'm going to be talking about information decomposition and phi and IIT 2. And then in part 3, I'm going to give an operational definition of synergy and phi. So I'm sort of trying to make some progress at least in all these 3 fronts. Okay? And each one of these parts are based on these different papers. If you're the kind of person that likes taking pictures of slides, this might be a good one to do so. So this paper is a PRE paper from last year. Part 2 is from a paper that's in the archive. Part 3, the paper came out on the archive exactly about 4 hours ago. I expect all of you to have read it by now. Sure, yeah.
We will, for those speakers that send us something, we'll put it on the website.
Yeah, and this last one also has an associated GitHub repo to all the code to compute synergy and all the good stuff. Good. All right, then. So let's talk about synergy and complexity broadly. Right. So then to do that, let's go back to basics, right? Because again, what we're facing here really is a problem in multivariate statistics. Great. So let's now try to step back and think about multivariate statistics and multivariate interdependencies, and let's see what can we learn and what are we missing. So if you have 2 neurons, or I'm going to say neurons because I come from a neuroscience background, but I think we're going to just random variables. If you have 2 neurons that can either be correlated or connected or not, and this is measured by the mutual information. Right? So really, the mutual information, you can see it as a log likelihood ratio of how likely is it that these neurons are connected or not. Thing is, if you have 3 or more neurons, suddenly there's qualitatively different ways in which these neurons can actually be connected. Right? So in one case, let's say we have 3 neurons connected in such a way that when I cut one of these out, or I marginalize it, or I don't observe it, I lose the connection between the other 2. Or I could also have it such that when I cut one of these neurons out, or I marginalize it, the connection between the other 2 remains. So these are qualitatively different modes of correlation between these neurons. The one on the right, I'm going to call it synergy. And the one on the left, I'm going to call it redundancy. And the meaning of those will become mathematically clear in a few slides. Okay? Yes?
Is it related to head-to-head node or head-to-tail node in Bayesian network?
Partially, but Bayesian networks are a bit underspecified. Like Bayesian networks won't tell you if some dependencies are redundant or synergistic. You can express these things very well with factor networks. Good. All right. So one natural question that might come up is, well, can we measure somehow the balance between this synergy and redundancy? If I observe a joint probability distribution, can I measure the balance between synergy and redundancy? The answer is yes, with this measure called the O information. That's basically just the difference between the total correlation and the dual total correlation. These are both like multivariate extensions of the mutual information. And so for a long time, people knew they existed and they were different, but they didn't know exactly what or why. And we sort of show a bunch of properties of this thing in this paper. For those of you that know this object called the co-information, this is basically a multivariate generalization of the co-information. That doesn't make any bloody sense for more than 3 variables. This one still does.
So that means the O information for 3 variables is the co-information.
Yes. So the O information intuitively is so there's balance between redundancy and synergy. So for example, if you have 3 variables that all are copies of each other, so they're either all on or all off, the O information will be positive. Or if you have 3 variables related by an XOR gate, meaning that if you know 2, you can predict the third, but if you only know one of them, you can't really do anything, then the O info is negative, indicating redundancy. So this is the exact same thing that the co-information would do, but this actually works for n variables in either side. And just to, now that we have introduced this like broad measure of redundancy and synergy, I think it's useful to compare it with some other measures that have been proposed, especially in the neuroscience literature. And I really like this old paper by now from 1994 by Shannon, Spons, and Everman. I think it's actually quite seminal, one of the first few papers to start bringing in a lot of the ideas from complexity science into consciousness research and theoretical neuroscience. So in this measure, in this paper, Shannon, Spons, and Everman talk about this measure called neural complexity, which is supposed to be quantifying to some degree the balance between integration and segregation in neural dynamics. And this is basically the precursor to all the phi type measures that have been developed since. And this measure of neural complexity, CN, basically says, well, what you have to do to compute this thing is split the system in all possible bipartitions and compute how correlated the system is across all of these possible bipartitions and take some funky weighted average. And then somehow if the system is fully disordered, meaning every variable is doing its own thing, then all of these mutual informations will be 0. And if the system is fully ordered, then only some of the mutual information will be non-trivial, and then you will also have overall a fairly low value of this thing. That's the idea how they present it in the paper. Now the thing is, if you read the abstract of this Shannon, Spons, Everman paper, they say we express functional segregation in terms of the relative statistical independence of small subsets of the system, and functional integration in terms of significant deviations from independence of large subsets. So if you come from this point of view of synergy and redundancy, it's really hard to read this and not think immediately of synergy. Right? So one thing we can do is basically compare Shannon, Spons, and Everman's original measure of complexity with this O information of ours. And we do this in this sort of mixture system where we have a copy on one side and an XOR on the other side, and we linearly interpolate between the two. And what happens, actually, is that the O information, as one would expect, picks up this transition from redundancy to synergy, because it goes from positive to negative. But the Shannon, Spons, and Everman complexity measure doesn't actually care. It assigns the exact same complexity to both of these completely different distributions, which again have sort of the same overall interaction strength, but again that sort of misses the point because it's a different type of interaction. Right? So the insight we get by studying this sort of synergy and doing this sort of going back to the basics in multivariate statistics is that these sort of integration and segregation, or this statistical independence of small subsets and deviations from independence in large subsets, these are not opposing forces. And synergy solves this apparent contradiction between integration and differentiation. In fact, if you do a little bit of math, what turns out is that actually neural complexity is much closer to the sum of these two quantities, the total correlation and the total correlation. So you can see these two quantities, this O info and neural complexity, as sort of change of basis from these other two multivariate extensions of the mutual information. So in this way, we can basically use multiple dimensions to describe neural dynamics. Right? So collapsing all of the richness of how could this set of variables interact, collapsing them into a single number, it doesn't seem to really make the cut. Right? So things could be more ordered or more disordered, and disorder could be more synergistic or more redundant. And now we're starting to develop tools to actually measure this type of thing. Okay. So interim conclusion for this part one of the talk is that integration and differentiation are not necessarily opposing forces, and that understanding synergy allows us to formulate multidimensional descriptions of complex systems. All right? Any questions so far?
So you didn't explain how you derive the all information. But,
no.
I thought that you can derive it via information decomposition in a general framework. No?
So what happens? Yes, but what happens basically from this formula is, and that's all in this paper, you can basically do a lattice decomposition of these two quantities, and it turns out that the information is a sum of redundancies minus synergies of every partition of the system. Right? I will get to that in a few slides, and then I'll point it back to this. Okay. Anything else?
Is it with some approximation or calculate that?
This is exact. Yeah, and you can compute these things only with basically linear combinations of entropies of the system. So for now, we're all fully within Shannon theory. Okay. Yep. Okay. So now let's move on to part two, and let's talk more explicitly about information decomposition, or PID. Okay? Which is a topic that I know that several people in the audience, for example, including Christoph, have worked on in the past, and it's a problem that I personally find super interesting. So what is information decomposition business about? In PID, or in partial information decomposition, the basic setting is the following. We have two predictors, x1, x2, and we have one target, y. And we have something like the joint predictability, so how much can I predict y by looking at both predictors together, and the marginal predictability, so how much can I predict y by looking at each predictor separately. Okay? And what happens is that sometimes the whole can be greater than the parts, meaning that I can get more predictability by looking at both of these at the same time than I could get by looking at either of them separately and then summing those two missing informations together. Right? And then the partial information decomposition, or the PID postulate, is that basically what we're going to do is we're going to split this mutual information in 4 different parts. There's some information that's redundant, basically redundantly held by both predictors. There's some unique information that one of them has but not the other. And then there's the fun bit. There's some synergistic information that you only get when you look at both of the predictors at the same time. Okay? I don't want to get into a lot of the details, but mathematically, this sort of goes by you define an intersection information. That's sort of how much information do a bunch of variables have in common. Then you set up this lattice thingy that says that, well, the information that 1 and 2 have in common must be less than the information that 1 has on its own, or that 2 has on its own, and those must be less than the information that they have together. And then you do this sort of Modi's inversion to get a partial information atoms, blah, blah. And then overall, this yields this system, this underdetermined system of equations. Right? And this is why this thing is really problematic, right? Because we have these 4 atoms of redundancy, unique, and synergy. That's 4 quantities, but Shannon theory gives us 3 of them. Right? So it gives us these 3 mutual informations. So we have 3 equations and 4 constraints. Sorry, 3 constraints and 4 unknowns. And this is tricky, right? This is why this thing is difficult. This is why we need more theory beyond Shannon. Yes.
Why do you call this intersection information? Is it not necessarily the same as the redundant information? Is it sometimes the same as the redundant information?
Yeah. So in Williams, this was introduced by Williams in a 2010 paper. In Williams' paper, they called that thing the redundant information. I have decided to adopt this more recent terminology from Artemi Kolchinsky in order to not confuse it with this atom at the bottom.
Okay. Okay. So.
Yep. Cool. So now we can, addressing your question, what we can do, for example, is if you write down this O information for 3 variables, it's basically just the sum of these 2 marginal mutual informations minus the joint, and then we just plug in these equations we just got from PID, and we get that the O information is equal to redundancy minus synergy. And this sort of justifies our earlier arguments about the O information being this balance between synergy and redundancy, blah, blah. When you have more variables, then what happens is that you can first split the system into a sequence of partitions, and then for each one of them, you have a sum of redundancies minus synergies, and the thing sort of generalizes for n variables. Okay? Now, thing is, let's look at phi. Right? And in particular, I'm going to talk about phi in this IIT2 sense, as introduced by Giannoni and Lucy in 2008, and also developed by Barrett and Seth in 2011. We have this measure that we're going to call phi whole minus sum, to distinguish it from several other proposed measures of phi. And this goes like that. So again, you have the mutual, how much can you predict the future of the system based on the past of the system, minus how much can you predict if you sum these 2 things on their own. So this thing looks a whole lot like that thing, except not quite. But we can actually, I mean, it does sort of beg the question of, is phi also related to synergy and redundancy? And how can we do that? We need an extension of PID to multiple targets. Because if you realize in here, all of the mutual information have this y at the right side, and in here we have y1 and y2. So we need to do a bit more PID theory, which we did. And we came up with this thing called FID, or integrated information decomposition. Basically means we can do the same information decomposition, but for multiple sources and multiple targets at the same time. How does this work exactly? So where in PID, we have this mutual information and we split this into this lattice. Now we're going to do the same thing, but we're going to have a bigger lattice that's basically the square. And now before we had redundancy, unique, and synergistic information, now we're going to have information that is redundant, unique, and synergistic in the past and in the future. Okay? So again, I don't want to dwell into the mathematical details too much, but it's basically just the Cartesian product of one PID with another PID. And now we can actually look at a few examples and hoping that that will sort of be slightly more intuitive. For example, in PID, you can decompose the marginal mutual information into 2 terms. So the information that x1 has about y is simply the redundant information that both that x1 and x2 have, plus the unique information that only x1 has about y. In PID, this decomposes in 4 terms. Again, just the square. Right? So we have the information that's redundant in the past and redundant in the future, and then with the redundant in the past and unique in the future, and all 4 combinations of these 2 things. You can do a similar thing for the joint mutual information, and you get 4 terms in here, and you get 16 terms in there. And you can do other interesting things, like, for example, with conditional mutual information, or in PID, you can write down the conditional mutual information as a difference between normal mutual informations, and you get a unique and the synergy. And in FID, if you do a transfer entropy, again, you get 4 terms that include synergies and uniques of various sorts. Okay? Now, what can we do with this? First of all, are there any questions, any burning questions about PID or FID so far? Okay, let's look at a few results. Yeah, yes.
I think I probably got lost at some point.
That is not unlikely. Yeah.
Good. It makes me feel better, I guess. So PID, all good.
Yeah.
FID, you introduced it because.
So our main wrong question. Our main motivation with FID was this, right? So is phi also related to synergy and redundancy, right? So can we split? The same way that up there we got these marginal and the joint mutual informations, I could split them in chunks and look at their difference to get some atoms and blah blah. could we do the same thing in here? And the reason we cannot use simply normal PID is because in PID, if you realize all of the terms in here have the same target variable, y, so to speak. Whereas in FID, you have here y1 and y2, and here's y1, and there's just y2. So the targets are different. Therefore, we cannot simply just do a normal PID. That was our original motivation for engaging into this. Okay?
Maybe, so if you have a multivariate Markov chain, you can only use this.
Yeah, basically. I think there's another question over here.
Yeah. Sorry, that very basic question.
Yeah.
I don't understand how you compute this redundancy and synergy part.
Yeah. So far I haven't told you, actually. So again, going back to this system of equation, things that this is underdetermined. Right? So we have 3 constraints and 4 variables. So you have to basically put something in. Right? You have to come up with a measure of synergy or redundancy or unique, and then solve the system to get the others. There's a bunch of measures that have been proposed. There's currently not a lot of consensus. And basically, I'm going to give you an exact formula to compute this later. But yeah, there's a bunch of people that have tried, Christoph among others, to produce some of these measures to calculate one of these, and then get the others by just solving the system. In general, it's an open problem. Okay. Good. Okay, so now looking at a few results. So one issue in IIT research is there's a bunch of these like phi-like measures proposed, and there's still no consensus on which one should we use or which one is better than the other. Right, so all of these measures have been proposed over the years, and they sort of appeal to different intuitions, or they use different mathematical tools, and they all satisfy the same like basic requirements of they are 0 in a fully ordered system and 0 in a fully disordered system. Problem is that if you actually compute them on some even very simple system, they can disagree wildly. Right? So what I'm doing here, I just have these 2 variables in a sort of coupled autoregressive process. So these variables are coupled with each other, and they have some noise, some correlated noise coming from the top. And I'm seeing here how these different integration measures change as I increase the correlation of the noise. And these different measures, they all do whatever. Right? So there's some of them that go down, some of them go up. And I mean, we can sort of explain why in many cases, but it's an issue, right? Like they differ, and sometimes in fairly mysterious ways. Another problem that has been pointed out is that if you look at this phi Holman sum, it can sometimes be negative. And that's tricky, right? Because if you come at this from a sort of IIT point of view of I want to see how integrated is the system, what does negative integration mean? That's certainly not desirable. So what you can do with phi-ID is you can basically get a bunch of these measures, and you can say, well, what of these atoms are they actually capturing? And then what we see is that actually these measures, they're different not only in practice, but also in principle. Right? So each one of these measures is capturing a different combination of these information atoms. Right? So it's not that they just differ in tiny details, they're literally picking up on different like information dynamics, or like different interactions within the system. Another thing you can do is, again, trying to answer the question of why is this thing negative sometimes. Do you have a question?
Yeah. So what's this?
So
two of yours are also exactly the same.
Yeah, these 2 are the same. Yeah. They still differ. Because so again, there's different ways of computing each one of these things. But in general, so some of these 3 at least can be written as linear combinations of these guys. And these 3 we can perfectly explain their differences. This one, we're not entirely sure yet because it's not an exact combination of these things.
Why are you saying these multiple? So 1, 2 to I means there's multiple. I can use multiple of those type of objects and combinations of them to get phi, and then a different combination to get CD?
Yeah, so this is phi causal density and another measure called psi, which again the details don't fully matter. And this basically says that phi is a sort of combination, has a negative component of this like particular atom, that is sort of redundancy in the past and redundancy in the future. And then it has a positive contribution from each one of these atoms. Right? So different of these measures have contributions from different types of atoms. Yeah, exactly.
Zero means no contribution.
Correct. Yeah. Okay. So another thing you can do is sort of if we take the formula for integrated information, this phi whole minus sum, and you replace all this stuff by the corresponding atoms, we can decompose phi whole minus sum, and we see this interesting thing where actually we get a whole bunch of synergistic atoms. We get some atoms with the unique information that's transferred from 1 to 2 and from 2 to 1. And interestingly enough, we get this negative atom in here, which is this like double redundancy atom with a negative sign. That's basically double counted in these two things. Right? And it basically explains why, under or in what conditions, phi can be negative. Like this one particular version of phi can be negative. Right? And if we want to fix this, basically if we want to make it non-negative, we get the thing, we add the missing bit, we run it on the exact same system as before, and bang. We basically lift it up, and now it becomes non-negative as you increase the noise correlation. Right? So we can sort of use this to reason about these phi measures and sort of pick and mix what effects we want to capture and how, and just add them together. And that's it.
Can you go one back?
This.
Okay. Do you know if this phi ms is phi WMS? Is
This
it
phi whole minus
not
sum?
the new one? Oh wait, the new one you construct. Is it the same as stochastic interaction? Do you know what
Yeah.
that is? No?
Yeah, so this is the phi that was originally proposed in the Balducci and Tononi 2008.
It's not the phi G by
No.
Izumi.
No, that one is not an exact combination of these atoms. I think it's related in some interesting ways that we're trying to find out, but it's not exactly one of these. Okay. Yes.
Each atom is underdetermined, right? So how do you compute corrected version? I mean, to compute corrected version, we need to compute the
Yes.
atom. Yeah.
So in this particular case, I'm doing something very, very simple, which is that I'm just taking this redundancy to be the minimum mutual information across every, each one pair of variables in the system. And I don't think that's a very clever way to do this. And I'm going to talk about a clever way very briefly later on. But yeah, there's several papers with proposing ways of measuring this. And we just,
Possible way to compute that.
yeah.
So with this, information decomposition framework, you can interpret, whole minus sum measure, for example, and you can fix this, by adding some term. But is this, for example, this fixed, whole minus sum measure meaningful, or you can come up with better one, like from bottom-up manner?
You can totally come up with better one in terms of the interpretability of these measures. I'm going to talk about that in the next few slides.
Okay.
Yeah. So one very quick thing before I go and address this for like the last 5 minutes of the talk is that something else that comes out of this framework is that phi typically captures fundamentally different phenomena, right? So for example, just have these 3 example systems that have the exact same phi, but they're qualitatively different, right? So I can have a system where basically all it does is to transfer information from one variable to the other, or one where the feature of one variable is the XOR of a bunch of others, or this weird one where the XOR of these three determines some collective property of the feature, but not any one of them. Right? So for all of these systems, phi is exactly the same, but they each have different, one of these like different atoms on, so to speak. Right? So if you wanted to like compare these systems in terms of how much they integrate information or how they integrate information, if you were to just look at phi, you would be making a sort of apples to oranges comparison. Right? So by looking at this PID, we can get a sort of more nuanced picture of the system. And this is what I meant earlier on by systems can deviate from independence in meaningful way, in different ways. So of course, if you have any prior theoretical or experimental reason to say, you know, I want to collapse all my system down, all my systems in one dimension, and I want to just compare a scalar, you can do that if you have any good reason to. But if you just want to study, you know, if you just want to have accessible tools to compare information dynamics in a bunch of systems, I think this is something to bear in mind.
Can I ask it?
Yes.
So what's all the so the last part you explained the two-body program, I think, in the sense that the two nodes, and you explained the several atom, different kind of atoms. So what's the is the number of atoms increase with the number of nodes linearly or exponentially, or?
Oh, very quickly. It increases very quickly in general.
Okay, so now you say seeing atom capture the property of network. Is it easy or a big?
You can make, typically computing all the atoms is a pain in the neck, but you can compute reasonable summaries that have good properties. So you can sort of aggregate. Yeah, you can aggregate some of these atoms in nice ways. So we have some of these measures that are actually scalable and sort of relatively efficient. Computing all of them in general is like only possible for like very, very small systems. Yeah. Yep. And these names here of like transfer, downward causation, and causal decoupling, those will make a lot more sense, I hope, after or during Fernando's talk. Okay. Good. So as an interim conclusion from this part, one, we proposed this phi-ID as a unification of IIT and PID, and two, phi measures a mix of different effects that can be disentangled with phi-ID. Okay. Question? Yes.
So you basically say that there is no reason to invent one unique phi which integrate everything, and we should look at different things depending on what we want to see?
Yeah, basically.
So one number is not enough?
Yeah, totally. That's, I mean, well, you could still say, right, like if I have my Julia hat on, I could still say, well, consciousness is one thing. Or like, say, let's say that you're interested in IIT because you're interested in consciousness, which is a very interesting thing to do. You could still make the claim that I want to associate consciousness with this one scalar number, and I can still measure it because it's an interesting thing to measure for other separate theoretical reasons, right? Or because it has experimental predictive value or for some other reason. If you're just interested in looking at the system and seeing what's going on, or like finding reasonable measures to describe interactions between parts of the system, blah, blah, then I think this multidimensional approach is much more fruitful than just having a scalar number. Does that make sense? Yep. Okay. Yeah. Sorry.
We can consider information decomposition for inverted time arrows. I mean, from past, future to current state.
Yes.
Then, is there any clear relation between this time arrow decomposition, this time decomposition?
Yeah, that's a very good question, actually. So the way you get this phi-ID is precisely by taking the product of those two. Right? So you do, the way you get this PID is by doing a decomposition from the past to the future, and then another one from the future to the past, and then taking the Cartesian product of those two. That's precisely how it's done. In that somewhat like obscure diagram. Okay. Good. So now in the last 5 minutes, wait a minute, slides. Yeah. Well, are we keeping track of that? Yeah.
Of course, I'm keeping track.
You have 8 minutes.
Good. Yeah, so in the last 5 minutes, real quick, we're going to talk about this thing called synergistic disclosure, which is addressing some of the other questions that had come up, which is how do you actually compute this thing and what does that mean? Right. So when I tell you that this phi or this synergy or whatever is like 0.8, what does it actually tell me? Can you frame this as an actual information-theoretic problem? And the answer is yes. And we're going to do this from the perspective of data privacy, like privacy-preserving statistics. And I'm hoping this will make, I'm just going to introduce the concept very briefly and then open it up for questions or go get a coffee. So the goal of this part of this sort of synergistic disclosure business is formulate an operational definition of synergy. That is a definition of synergy that has some information-theoretic meaning. And the way we're going to do this is in 2 steps. First, we define a synergistic channel. So let's say that we have, again, as before, x's are going to be the sources and y is going to be the target. And they want to generate some other variable v that is a function of the x's, and it's going to come from a synergistic channel. And what this, somewhat lengthy set description is that v has to be independent from any one of the x's. Right? So I'm going to make a variable that's basically a function of x, but that doesn't depend on any of the individual x's. Okay?
Okay. Yeah.
And then I'm going to take synergy to be the maximum information that I can obtain through a synergistic channel. And this is a perfectly operational definition of synergy. And this is fairly well computable. So that's, very briefly, that thing, like this set is related to the null space of P of X. And that thing is a simple linear programming optimization problem. Yep, and you can basically identify synergy now with basically how many bits can you transmit through this channel, and that's that comes straight from Shannon's source coding theorem. And so we give that an operational definition of synergy. On top of this, I'm not going to go into details, but you can also do the same lattice game. It's a slightly different lattice. For those of you that are into PID, we can go into details later. And for example, in the simple case where x1 and x2 are independent fair coins, this is super quick to compute, and this is the mutual information of the XOR between the 2 variables and the y, essentially. Right? And you can compute this for a bunch of simple probability distributions, and you get exactly what you expect, which is the XOR synergistic, the copy is redundant, and some other stuff. And there's an instant case here with the 2-bit copy. So the 2-bit copy is a fairly well-known distribution in PID research, where basically what we do is we just have 2 inputs, and the output is basically the concatenation of those 2 inputs. And there's lots of arguments to whether these things should be synergistic or redundant or what. And funnily enough, this one particular definition of synergy says that these 2 things are actually quite redundant, quite synergistic. So it says that the information that you can disclose about this pair of bits is maximal where the bits are completely uncorrelated. But there's a lot of arguments back and forth, but one of the nice things that come with this operational meaning is that now we can actually reason about this. You can say, well, if you have 2 bits, you can disclose their XOR without compromising either of them. And actually you can interpret this as a sort of synergistic capacity. The synergy that some bits have about themselves is this should be the other way. This is greater than the synergy they could have about anything else. So having an operational meaning is good, because we can actually reason about these measures in weird counterintuitive scenarios. You can also do this like funky coarse graining that we were doing before, which I'm not going to describe. And what we can do, basically, just as a quick sort of proof of concept, we can evaluate this thing on Gibbs measures of like distributions that have Hamiltonians of different orders, of like say order k, and basically as you increase the order of the interactions in the Hamiltonians, the synergy in this thing grows monotonically as one would expect. Okay, so we have this way of computing synergy that is matches more or less our intuitions in these basic examples, and it has an operational meaning that we can think about and reason with. And with that, I'm going to conclude by just mentioning that we have a similar thing for integrated information that basically says, well, you put a synergistic variable here and another synergistic variable here, and you optimize these two things jointly. So you have an efficiently computable file with operational meaning. And with that, I'm going to conclude. You can find the source code and the papers for all these things available online. And as a final quick wrap-up, PID and this O information are novel tools for information dynamic research. And this synergistic disclosure S brings a concrete operational meaning to synergy and phi. There's a bunch of references with all the papers, and that's it. Thank you very much for listening.
So we have 3 minutes, so if there's some question.
Why are you on? Can you say that?
Could you go back to when you define the synergistic channel? And could you repeat what the synergistic channel?
Yes, so a synergistic channel is basically a channel that potentially discloses information about the whole of X while being independent from any individual part of X. So it's sort of like disclosing high-order features that do not compromise the privacy, quote unquote, of any of the individual variables.
XOR being the two, the primary example, two.
Correct.
So if the xi's are 2, then XOR
is V.
Correct. Yeah. So you can define a whole set. Like the XOR is not the only function that is sort of synergistic, defined in this way. So then you can have a set with all possible synergistic channels or synergistic functions, and then you just optimize over them to see, well, how much can I learn about Y only through this synergistic channel.
So you have multiple possible synergistic channels.
Yes, and then you optimize over them. It just turns out that actually optimizing them is very easy. You can do this with the normal linear programming techniques.
What do you mean by? But you only have one variable V?
Yes.
But it can be arbitrary cardinality.
Yeah.
Okay.
Thank you very much. Super interesting. So I love this sort of mathematical rigorous analysis. Yeah. Meanwhile, so it's a naive question. So I'm curious. What is the ultimate goal of this sort of analysis? So do you want to capture the property of big system?
Yes. So
if so, then how to use this? So as you said, number of atoms increase exponentially. So if we anyhow capture some average property, right? Mm-hmm. Is there any magic that connects this one and big? So macroscopic view, mm-hmm. How to connect those?
Yeah. So that's a very, very interesting question. So what we can do, so again, as I said before, computing each one of these atoms all the time with these funky measures is a pain in the neck, and that's probably very impractical. But having all of this theory at the back allows us to make some very, very practical upper and lower bounds for things. Mm-hmm. And those are actually typically quite useful. So we're going to see examples of that in Fernando's talk after the coffee break. Yeah. What we're going to do is basically get all of this theory that we've done now and actually use it to study basically emergence in complex systems. And those systems are actually big, with like lots of things in it, but we can basically take these averages or coarse gradings and blah, blah, and get reasonable lower and upper bounds to bound some of these synergy and redundancy quantities into interesting ranges. So that's in practice, that's how we end up using all of this. We have the theory, and then we sort of take some instinct bits that are, that we can actually apply to real systems.
Thank you. Very interesting talk. I mean, the best bit was a bit fast towards the end, I have to admit. But I remember when I know you're familiar with Niels Bacina's work, where he kind of talks about the impossibility of the lattice given the axioms that are out there.
Yeah.
And so, if you're using your method now to derive such a lattice, do you know which of those things you're sacrificing, or does it?
Yeah, so I'm sacrificing the identity axiom.
Okay.
No, that's the one that says that the to-be copies should not be synergistic.
Okay, thank you.
Yeah. So, like, again, as I said, like, with this measure, we know that like it does assign quite a lot of synergy to the to-be copy, but we can actually explain why. So it makes a lot of sense. And so, in order to reason about this, I think this is a sort of unusual version of synergy if you come from this literature, right? So typically in the PID literature, what you do is you define a measure of redundancy, and then you compute all the possible redundancies, and you say, well, everything that I can't explain with redundancy must be synergy.
Well, it's a force.
It's the inclusion-exclusion principle.
Yeah, I mean, basically, if you define one of them, you have the other three things given from the Shannon inequalities, and then so everything falls out of it, right? I mean.
Yes.
Regardless if you do synergy, redundancy, or even unique information.
Yeah, slightly. But with those other, if you begin with a measure of redundancy, then you're sort of saying, this is the information I can obtain from low-order statistics, and synergy must be the rest. Whereas with this, you say, well, how much information could I get from high-order statistics? And then redundancy must be the rest.
Very interesting.
Okay.
If we have all the value of these information decomposition values, then can we uniquely specify probability distribution?
Very good question. I have no idea. I mean, for some of them, yes. I mean, for a limited subset. So if you know that your distribution is only purely synergistic, then you know it must be an XOR, for example. But in general, for like arbitrary values of the atoms, I have no idea. That would be an interesting problem to tackle.
So come back to my question. So how would you define phi, like with this information decomposition method? You can,
like that.
As I said, you can interpret existing values, existing measures with this method. But I think you can come up with the better one or something.
Yeah, so you can do two things, right? So, I mean, so one of the lessons that come out of this is that actually, if you are coming up with a measure of phi, it's usually a good idea to think about why you're doing it and what's your goal with that, right? And depending if you want to quantify only information that's transferred or information that's synergistic or how exactly, and then based on that, you can sort of tailor your measure to the specific phenomenon you are trying to study.
Exactly. So first we need to determine the purpose for measuring, phi, and then for this particular purpose, you can come up with some best measure or something.
Yeah, exactly. Which is a bit more of an engineering approach, right?
But, the philosophy of IIT, right? The Python is considering this kind of original philosophy, which would be the best.
Good question. I mean, if you want to make a measure that is discriminative of humans' like state of consciousness, then I think what you have to do is actually make something you can compute on human brains and just compute it and see how well it does, right? So again, this is all perfectly compatible with there being one particular measure that discriminates state of consciousness. Like this is all just math. It doesn't make any statement about brains or consciousness at all. It only says that if you want to study interactions between random variables, between like time series, here is an interesting tool to like think about it and mix and match and do stuff. Of course, it may well be the case, as Manoli says, is one combination that just hits the spot and represents something related to consciousness. That could still be the case.
Yeah, but we can discuss it later.
Yeah.